Hi, welcome to the Quant Zone. Today we're going to be doing another coin triplet count problem, but this time the twist is very different. Again, you have a fair coin, 50% chance of getting heads and tails, respectively. And we want to, this time want to compute the probability of seeing a pattern HHH before a pattern THH. Okay, and this is going to be an interesting problem. We're going to be going through Markov chains, but I think there's also another solution where you don't have to use Markov chains, and I will let you guess this, in the comments. So do let me know what you think about it. All right, so let's get started. So in this question, we have something called a triplet competition. So here we have a fair coin, and we'll keep tossing. So we either see one of these patterns, which is HHH or THH. That basically means if you see a sequence of heads, heads, and heads, then we stop the game. Or if we see a sequence of tails, heads, or heads, tails, heads, and heads, then also we will stop the game. And the question asks us, what is the probability we see heads, heads, heads before we see tails, heads, heads? Now, so you could also think about it like two players playing a game, and then one bets on seeing a head, head, head first, and the second one bets on seeing a tails, head, head first. Again, we were trying to find out which one, the probability of the first player winning the game. You could also think of it like this. Now, if you remember from some of the earlier videos that I talked about Markov chains, if a game stops, then you can think about it like, that you've reached an absorbing state, okay? And we know that here game stops in two places, either when we see a pattern HHH or we see a pattern THH. And okay, at this point, I would also say that, it's great if you can also watch the last couple of videos where we did the coin triplets and we try to find out, the expected number of tosses to get to one of these patterns. Okay, so this will help us to get, build a structure on this problem, and it will help you easily build a, transition graph here and solve this fairly efficiently. And one thing to appreciate before we get started is you can think about it like this: if you didn't have, if you didn't have the Markov chain structure here, solving this problem can be a bit difficult, I must say. And I mean, it's definitely possible to try doing this using conditional probability and other probability-based approaches. It's possible, but I think it's got to be more complicated as compared to Markov chains, as we see here shortly. Okay, so let's quickly get started. I'll just write a few things. One is, let's try to figure out, what kind of absorbing states we have. So absorbing states are head, 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 and also tails, head, head. Okay. We'll talk about the transient states in a second. Let's first try to build a transition graph. Now, again, if you've not seen the previous two videos, I would highly recommend you go watch them, because I'm going to be using the same approach, of building the transition graph here without directly building the transition matrix, okay? So let's say this is the starting state, and starting state is basically when you've started the game, okay? No coin has been tossed yet, and, there are two approaches, there are two possibilities here. Well, first thing is, it's a fair coin, so probability of head is half, that is also equal to the probability of tails, okay? Now, it's a fair coin, and one of the two possibilities is, we get a head or we get a tail. Now, why do I mark them separately? Because, you have two patterns here. First pattern is HHH, and it begins with H. So getting the head in the first place, or in the first toss, is helpful, and we should mark it as one of the states. Then the second one is tails, head, head, right? This is another pattern we're looking for. So if you see this also begins with tails, so therefore it's also important to mark this as a second state here. Okay, so, well, the probability of reaching from starting state to heads is half, and the probability of reaching from starting state to tails is half, because it's a fair coin. Okay, what is a possible situation here now? So let's now try to understand this. Let's say you got a head first, okay? So we're in this state. Now, after head, it's possible you get a head, head. That is basically the second toss is also a head, or it's possible you get a tails, okay? So if you're in this state, let's say if you're in HH state, then you're definitely progressing towards the pattern HHH. What are the patterns? HHH. This is what we want to target. You're progressing towards that. Okay. So we should definitely mark this. But if you, let's say, so let me just quickly go back and mark this on the transition graph. So possibility of reaching HH state, again, it's half, because for the second toss that you do after reaching state H, or, to get another head after reaching state H, is actually, the probability of that is half, as you can see here. Now we're going to talk about the second case, which is if you had a head in the first toss, you've reached state H, now you get another toss and you get a tails. Okay, so now you're here. Now you see that you're not going to get head, head, head via this pattern, because, you've already gotten tails, right? But what you see is the other pattern we cared about in the absorbing states, as you can see, is tails, head, head. So if you get a head, tails, then what that means is this pattern, this can progress you towards tail, head, head. Okay, so this definitely takes you towards the tails part. Okay, so now you may be thinking, why does it not take me to the starting state? Well, the reason is because once you have a tails here, if you get another tails, that's okay. I mean, you still have a first tails for THH pattern. But if let's say you get THHH, then you have a tails head head pattern already happened, right? So, therefore, from head, you don't go back to starting state. You actually go to the tail state with half probability again. Okay. Okay, now let's try to understand what happens from tail. Okay, now think about it from tails. What are the possible situations? So we've covered this. Now we're talking about tails. So in tails, two possibilities again. Either you get a tails head or you get a tails. Okay, now half probability for each because it's a fair coin. Now if you're looking at TH, now this is progressing towards the pattern THH. Okay, so this is very good. But if you look at the other case, so this was the first case, this is the other case, TT. Okay. Now in TT, what's happening is you're definitely not progressing towards HHH, right? Or you're not even going closer to that. But if you look closely, what you see is that if you ignore the first T, using the second T, you still can get to THH, right? And as long as you keep, let's say you keep getting T, that's okay. But it doesn't matter because for our pattern, for our Markov transition graph here, we are progressing towards THH, and what we need is T at the start. So if you get multiple T's, that's okay. You're just still being state T here. You can't go to state H. You can't go to, you cannot go to state HH. The reason is because you already have a T at your back, right? The moment you get H, you're in state TH. If you get another H, you're in THH state, which is an absorbing state. But if you get, let's say, a THT, then you're back in T state because, because this last T can be used again to reach the pattern THH. Okay, so let's quickly represent this on the graph. So, two possibilities. If you get a head from tails, you get TH. But if you get a tail from here, you're basically in the same state. Okay. This is the case, so this is the case when you get a TT. This is the case when you get TH. So now let's talk about HH case. So if you're in HH, now two possibilities. Either you get a head, either you get a head or you get a tail. Okay. Now probability of each of these cases is half. So if it's a head, then you will get a head, and you've reached the pattern HHH. The game stops. That's the condition we saw here. Okay. And let's say so let me just quickly actually write this on transition graph. So if you get another head from here, again, it's a fair coin toss of probability half, you will reach state HHH. Okay, and it's an absorbing state. You don't get out of it. So I'm just going to quickly, use an arrow to mark it that you can only stay in the state with probability equal to 1. What happens if you get a tails after this? And this is half probability here. You get a tails and you get something called as HHT. Now the question here becomes, the moment you get a tails, you can never go back to HHH. That is one of the interesting part of this problem. The reason is, let's say you had HH and you got a tails. Okay. Now let's say you have HH, so it's a THH pattern, right? You can never have HHH pattern because if you have one tail, if you have any occurrence of tail in this game, to reach HHH, you need 3 heads. But before you get 3 heads, you will get 2 heads, and THH pattern will get complete before HHH pattern gets. Okay, so that's the reason when you are HHH, when you're in HH, this state here. If you get a tails with a half probability, you actually come back to the state here, the tail state. Okay. Now let's talk about TH. So again, half probability, you get THH, you get a head, and half probability, you get a tails, which is THT in this case. Now, similarly, THH is one of the absorbing stage patterns, so the game is going to be over. But if you reach the tails here, essentially you go back to the tail state because THT is none of the patterns we care about, or the game stops there. But the moment you have THT after this, if you keep getting tails, you're going to be stuck in this state. But the moment you get a head, you'll start moving towards THH pattern rather than HHH pattern. Okay, so let's quickly represent this. So it's half probability, you get THH, and THH patterns game stops, so it's an absorbing state, probability 1, you stay there. But let's say if you don't get ahead in TH state, we're we're right here. If you don't get ahead, then you basically go back to the tail state. I'm just going to mark this, right? So this is, I would say, the transition graph for this game, where you have 2 absorbing states instead of 1, and, HHH and THH. And we want to see the probability of one happening before the other. So anytime you get a question like this, you have to understand it can be represented as Markov chain. And if you want one event to happen before the other, and the game can stop in any of these 2 events, then you have basically absorption states, and you can model it like this, and then we will solve this from here on. Okay, so I think now it's a good time to basically give it a shot and try to solve this yourself. And again, the hint here would be to use absorption probabilities equation that we discussed in the Markov chains or some of the other questions as well. And I'm going to be linking the videos in the description for you to review if you're feeling a bit rusty on them. Okay, so I hope you got to the answer. In case not, that's okay. We'll solve this together. Okay, so let's not talk about the state space here. It's easy to see the state spaces as, there's heads, there's tails, there's heads, there's tails, heads, and there's the last 2 are the absorption states, heads, and tails, head. Okay, so these are the transient states. So if I'd say transient states, they're basically the starting state, the heads, tails, and the HH and the TH state. Just entire graph here, right? It's captured by the transient state. Okay, now, if you go back to the question, what you see is we want to see HHH before THH. So essentially what we are saying, if you have to parse this question here, what essentially it means is what is the probability that we get absorbed in this state here, HHH, and we don't get absorbed here? I mean, if you get absorbed here, you can't get out. So basically HHH will happen before THH. Because if you're here, you're here. You can't get out. That's the definition of absorbing state. So what we understand from that is our target absorbing state is HHH. Okay. Now we'll use equations of absorbing states, and okay. So we know, now I'm going to be using a different color. So AI is probability of getting absorbed in HHH when in state I. So if you're in state I, what's the probability to get absorbed in the state HHH? Okay. So if you look at the absorbing states here, so for absorbing states, a HHH is going to be 1. What that basically means is the probability you get absorbed in HHH if you're already in HHH. Well, if you're already in HHH, you're absorbed and you cannot get out. You would be there, so you're already absorbed. So that's why it's 1. But if I talk about the other absorbing state, just THH, that's 0. You know why? Because, this means what is the probability? This is probability of getting absorbed in HHH if one reaches THH. And I think the answer should be obvious because THH is actually one of the other absorbing states, as you can see in the graph here. So again, if you reach that THH, you cannot get out. You have to stay here because there's no outgoing arrow. The only outgoing arrow is to itself with probability 1. So this transition graph is actually a probabilistic approach. You start at starting state and you can reach either here or you can reach here. Okay, and the path can be different, but it depends on this probabilistic movement. And again, this is going back to the basics of Markov chain. The variables can take a different state as the time passes by, or as we take different coin tosses. But if you go here, what you see is if you are in THH, you cannot get absorbed in HHH, and that's what's represented here. Now for transient states, Okay, and again, the transient states are S, H, T, H, H, T, H. These are the transient states as we had covered here. Okay, the equation becomes like this. So now AI is sigma j Hj, probability of Ij. Okay, so again, this is one of the standard equations we've used for computing the probability of getting absorbed when you're in state I, and it's a transient state. So this is J spans across all the state space. J is all the state space, including the absorbing state. Why? Because we're saying from state I, you can go to one of these states, state 1, 2, all the way till M, all the possible states in your state space. Here it is from I, you can go to S, you can go to H, you can go to T, you can go to TH, you can go to HH, you can go to HHH, or you can go to THH. These are all the possible states you have. If it's possible to jump or not, that is determined by the probability of transition, right? That is determined by this probability here. And if you reach there, then what is the probability of getting absorbed from that state? That is represented by this part here. So that's how we got this equation. Okay, so let's quickly do this. For AS, this is going to be equal to AS times probability of SS plus AH times probability of SH. Okay, so this is basically including all the states here. And I mean, this is probably the first equation, that's why I'm going into details, but otherwise you can just go and look at the transition graph and understand which states is it possible to jump from a given state. And also if it's basically one of the other absorbing states, for example, here, this is going to be 0 because as we had, covered here, the probability of getting absorbed in HHH, given you're in THH, it's going to be 0. So this last term can be taken away. And if you go to the transition graph, you see from state S, you can either go to H or you can go to T. Any other states, there's no direct path here. You don't see a direct arrow as such, or like this. So therefore, this equation would just have, a couple of variables on the other side, which is AS is going to be AS. You can't stay in the same state as well. So this is also going to be 0. So this is AH times 2 plus AT times 2, right? Everything else is 0 because the probability of jump is 0. And again, if you make a transition matrix, you will get this answer, but I'm just keeping it short here. Okay, so if you have to simplify this, this becomes equal to AH by 2 minus AT by 2 is going to be equal to 0. That's equation 1. Okay, equation 2 is AH. So now if you go to AH here, let's see which states can it go to, right? So it can go to T or it can go to HH, okay? Other states, there is no possibility. So the probability of jump to other states is 0, so I'm going to just ignore all of that. So AH is AT times probability from H to T plus AHH times probability from H to HH. Okay, now if it's a fair coin, anytime the probability is going to be half, so I can quickly write this as AH is AT by 2 plus AHH by 2. And then you can simplify it like this. AT by 2 minus AHH by 2 is 0. That's equation 2. Okay, then you have AT, the next one. If you look at tails, tails can go to itself, and tails have a lot of incoming arrows, but it can also go to TH. Okay, these are the two states you can go to. So AT is AT times probability from T to T plus ATH times probability from T to TH. This implies AT's AT by 2 plus ATH by 2. AT by 2 minus ATH by 2 equals to 0. That's equation 3. Next one is AHH. So if you look at HH, here HH can go to T or it can go to HHH. These are the only two possible states you can jump to, right? AT times HH times T, say HHH. This is all from HH to HHH. This is equal to 1. AHH is AT by 2 plus half. Because if you're in HHH, you are already absorbed. The probability of getting absorbed is 1. Okay, so this can be written like this. AT by 2 minus AHH is equal to minus half. And the way I'm writing this like this is because I'm going to be using row reduction method, in which the variable sequence is going to be similar to the space sequence of states we have used here. And it's going to be clear in a moment. Now for ATH, so you're here now, in ATH, you can go to either THH or you can come back to T. Okay, so T and THH are the two possible states. So it's AT times probability of TH to T plus ATH, ATHH, yes, times probability of TH to THH. Now, if you jump to THH, you won't be getting absorbed in HHH. So this becomes 0 because we already have the answer. For ATHH, that's equal to 0. So this whole term becomes 0. So this implies ATH is AT by 2. And this can be written as AT by 2 minus ATH is 0. Option 4. So I suppose we have to cover 1, 2, 3, 4, 5. That's this fifth equation. Okay. So, we already have answers for the absorbing states, that is AHH, HHH, and, ATHH. We already had answers for this. And if you see, basically in this, you have the state space contains the 7 states, it's 1, 2, 3, 4, 5 here, and 2 more states. So we have 5 unknown, states for which we don't have the answer to AI, right? So it's just a 5 variable and 5 equation case. So if I now basically translate this to a row reduction method, I'm just gonna, write a new matrix, which is something like this. And if I, draw the sequence of variables, it's going to be AS, it's going to be AH, it's going to be AT, AHH, ATH. And this one is basically RHS coefficient. Okay, so let's see the first equation. So it's AS minus AH by 2 minus AT by 2 equal to 0. So you can translate it like this. You can say this is equal to 1 minus half 0, 0, 0. Okay, second equation, AH, AT is minus half, AHH is minus half. So S is 0, AH is 1, AT is minus half, AHH is minus half. All right, as you can see here, AS is 0. I mean, basically, the coefficient of AS is 0, AH coefficient is 1, AT is minus half, AHH is minus half. Okay. Okay, so here is what you have after you basically translate all the 5 equations, the coefficients in the sequence of the variables, as we mentioned here, and also the right-hand side coefficient. Okay, so you can confirm that as well. Now we'll apply row reduction methods, to basically convert into an upper triangular matrix and then try to find out the values of these coefficients. All right. Okay, so in the first operation, what we do is we take this row and we subtract this from this one so that this coefficient can be gone. And because in the last row, you need all 4 of them to be 0. Here, you need 3 of them to be 0. So this is the first operation. The second operation is basically from the 4th row, you subtract the 3rd row so that this coefficient can be 0 here as well. And then you can have a proper upper triangular matrix. Okay, so all right, so let's now get this. So we have what you call as upper triangular matrix. As you can see, this is the main diagonal we have, and the drawing may not be the most accurate. Like the spacing may not be the most optimal, but you have the lower, all the elements up below the diagonal is 0, and this is the main diagonal which you have. And above diagonal elements are okay to be non-zero or 0 as well. Okay, so now what you see is using the, the variables. So if you see the variable sequence here, it's going to be the same here as well. You can easily find out the values. So ATH times minus half is 0. This implies ATH is 0. Okay, the second equation. So we just used this one. Now we're going to use this one. So AHH minus 1 plus ATH times half is minus half, right? So this is already 0, so you can subtract it, and AHH becomes equal to half. Okay, Great. Then you have the next one, which is AT times half. So the third equation is, it's AT by half minus ATH by half is 0. Again, ATH is 0, so you can get rid of this. AT also becomes equal to 0. Okay. Then you have, you have AH times 1 minus AT by 2 minus AHH by 2 is equal to 0. Because if you see the coefficient here, this is for H, this is for T, this is for HH, and this is for DH. Okay. Now, what you see is basically AT is already 0. We computed here, so this goes away. And this becomes equal to AH is equal to AHH by 2. So AH is 1/4. Okay, cool. And then we're in the first equation, which is right here. Okay, so this is AS times 1 minus AH by half minus AT by 2. As you can see, the coefficients here is equal to 0. So again, AT is 0, so we'll get rid of this, but AS becomes equal to AH by 2. So therefore, AS is equal to 1/8. Okay, so we have all the values we're looking for, and I'm just going to quickly summarize this. AS is 1/8, AH is 1/4, AT is 0, AHH is 1/2, and ATH is 0. Okay. Right, these are all the values for the transient states, right? Now, if you remember, we want the probability of getting absorbed in HHH when we start the game, because that's where we were looking for, right? So this is actually equal to the probability we see HHH before THH. Right? Okay, so that is nothing but equal to AS. That's 1/8. Right? So I hope you got to the answer. If you did, that's perfect and fantastic. I would say you're now competent to there's some of the complicated questions in probability, especially the coin tosses, right? And if somebody were to say in this game, let's say the first toss is head, it's already given. Then you can also compute the conditional probabilities. It's simple. So let's say if the first head is given head, that basically means we're looking for AH, and the answer is going to be 1/4. Okay. But the answer to this question is 1/8. All right, so I hope you enjoyed this video. And if you did, please give it a like, share your experience in the comments. Also share the video with your friends and family. And if you have not yet checked out my playlist on brain teaser out, I would highly encourage you to check it out, because it's library where I'm going to be adding all the different kinds of brain teasers which you may encounter in your next quant interview. And if you're not so far subscribed to my channel, I would highly appreciate if you could do so. And until then, see you next time.